In this video, we're going to refresh on central limit theorem and sampling distributions. Every time we conduct a hypothesis test or a confidence interval, we're using a sampling distribution. And typically when we get to this point in the year, I realize that a lot of you guys didn't pick up exactly what a sampling distribution was from the first time we went through it back in chapter 18. So we're going to refresh and make sure we understand what really the foundation is in all these inferential procedures are, the hypothesis tests and confidence intervals. Now, a sampling distribution is called a sampling distribution because, as indicated by the name, it's a distribution built around the sample. Now, to get some vocabulary out of the way, a sampling distribution of the mean is an unbiased estimator of the mean. And we say this because regardless of the size of our sample, our distribution is going to be centered around that true mean of the population. So in other words, our sample is going to do a decent job of estimating that population parameter, that population mean, regardless of its size. It's not always the case. So let's say we're trying to estimate something other than the population mean. Okay, so in some cases, we're going to do a bad job at estimating the parameter, in which case we would have what's called a biased estimator. So a biased estimator is just saying that we're not doing a good job estimating what we're trying to estimate from the population. If we're estimating the mean, it's unbiased. So if, for example, we're trying to estimate the range of a population, so range of, say, incomes, okay, and we're trying to estimate it by taking a sample. The only way that we're going to estimate the range accurately is if in our sample we take the minimum and maximum value as two of our sample values. If we miss either of those or both of those results, we're going to get a range that's smaller than the range of the population, and we're going to have a biased estimator of the population range. So like I just said, we're building these sampling distributions around the sample, but to do that, we need to meet three conditions, and these are the same conditions that we used for all those hypothesis tests and confidence intervals. So first off, we need to meet the randomization condition, just saying that the sample must be a simple random sample of the population. 10%, sample can't be more than 10% of the population. These two conditions are just verifying the independence of our sample items. The third condition depends on the type of problem. So we have categorical problems that are proportion problems, and we have quantitative problems, which are X-bar problems. So for categorical proportion problems, we have to check the success-fail condition. We're going to do n times p and n times q. We only have a p and a q in these proportion categorical problems, and we want to make sure that the number of successes and failures is at least 10. For quantitative problems, we're going to check the nearly normal condition, and there's a few different ways we can do this. So to start, if it gives us data, we want to actually look at that data. So sometimes it'll give us a plot. Okay, it might be a histogram. We're looking to see, is it approximately normal? It might be a normal probability plot. We want to see, does it make a straight line? If it's just raw data, we typically want to make a normal probability plot in our calculator, and we want to see it making that straight line. And we'll just say it's reasonably straight with no outliers. Okay, if we don't have data, we're looking for one of two other things. So if it says in the problem that the original population is approximately normal or normal, then our distribution of sample means, or sampling distribution, will also be approximately normal. Okay, so we look for something with this type of wording. Okay, if it doesn't say that, we need a sample size greater than 30. Okay, if our sample size is greater than 30, the central limit theorem applies. Once we start averaging all these numbers, we're going to get values that are consistent enough that when we start piling them up, they pile up around that true mean, and it gives us that approximate normal model. Okay, so these two conditions are both about verifying normality of the data and allowing us to use that z-score or t-score for the test statistic. So for example, we have this graph here. This is displaying family incomes from over 12,000 families from a county in Connecticut. We can see it's heavily skewed to the right, as most graphs of income are. It ranges from about 17,000 to 267,000, so a very big range there. The mean of all 12,000 values, so this is our population mean. We would label this as mu. is 76,700. And the standard deviation, again, of the population, so this would be sigma, is 40,100. Now, since it's so heavily skewed, we couldn't do anything with z-scores or find probabilities with normal CDF because we need an approximately normal distribution to use z-scores and normal CDF. So rather than look at this heavily skewed distribution that we can't do anything with because we can't use z-scores or normal CDF or anything that we would normally do, instead let's take a sample. So let's take a random sample of 100 values from the over 12,000 families in our distribution, and we'll simplify it to a single value, an average. We get 75,151. And then we'll do the same thing again. We're going to take a different sample of 100 values again, and we get another average. And then we do it again and again and again, each time taking 100 random values from our distribution and each time averaging those 100 values. So what we're starting to do here is we're starting to create a distribution of our samples. We don't care about those original 12,000 values. Instead, we care about what's the average that we're getting when we take 100 values from that distribution from our sample. Piling up all of these averages, 5 shown on the previous page, and if we just keep going, keep going, keep going, this histogram here has 90, and we can see it's starting to take on that normal distribution shape. Okay, a true sampling distribution isn't just going to stop at 90. It's going to go through every possible combination of 100 values that we could pull from that 12,000 family data set. So there's going to be a huge number of 100 value samples, all simplified to single value averages that all go into creating this distribution, and that would become normal. If the sample size is large enough, and by large enough as a general rule we mean greater than 30, this distribution will always be approximately normal. Also, just a note, we always want to use the word approximately before we say the word normal. It's going to be centered around the true population mean. So a few slides back when I showed you that heavily skewed distribution, I told you that the mean was 76,700. And we can see that's right where the center of this curve is. Okay, that's not just by chance. That will happen every time we do this. The standard deviation is going to shrink. Okay, it was 40,100, and it's going to shrink by the square root of the sample size. So we divide it by the square root of the sample size. The larger the sample gets, the skinnier our normal curve gets. We get more consistent results with larger samples. Now, normally we don't go through the trouble of taking multiple samples. We'll just take one sample of size n, and we find the mean and the standard deviation of that sample. So let's say we get that mean, that standard deviation. We take that one sample and we build our entire sampling distribution around that sample because we don't need multiple, we just need one. We take the mean, and the mean goes right in the middle. Now, we don't know that the true mean is 76,700, right? So whatever we get from our sample, we just put in the middle. And we can do that because the mean is an unbiased estimator. All right, so that's just going to go right in the middle of our sampling distribution, and whatever we get for our standard deviation, we're going to change by that equation. We divide it by the square root of the sample size, and that gives us our distribution, our sampling distribution. Those were all for quantitative problems, but it works pretty much just the same for categorical proportion problems. Let's say we flip a coin 10 times, and we find the proportion of heads that we get. In this case, we got 5 out of 10 heads, exactly what we would expect when we flip a coin 10 times. So we have proportionally 50% heads. If we do this same thing over and over and over again, flip a coin 10 times, right? Put another dot on the graphs. Maybe we get 4 heads out of 10. Maybe we get 7 heads out of 10. The dots will start piling up. That would create our sampling distribution. So here's a sampling distribution of 100 trials. Each of these dots represents 10 coin flips, okay? And we simplify the 10 coin flips to a single proportion value. So for example, this one over here, in this trial, 9 out of the 10 flips were heads. Okay, so all of these dots were 10 coin flips. We switch them to a percentage, and just like before, we see that normal model taking shape there. Okay, we can see that it's centering around that true proportion of what we would expect to get when we flip a coin and we count the number of heads or find the proportion of heads. And just like the quantitative problems, we don't do this a bunch of times. We just do it once. So we would flip the coin 10 times. We would do one trial of that, and we would switch it to a single p hat. So let's say we flipped it 10 times and we got 6 heads. So our p hat would be 0.6. That's going to go in the middle of a curve. Again, we can do that since the mean is an unbiased estimator. And the standard error is going to be given by this equation for categorical problems. You should recognize it from both confidence intervals and hypothesis tests. So we plug in our values and we have our distribution. As mentioned on a previous slide, for all these sampling distributions, the standard deviation shrinks as the sample size grows. This is an important concept to understand because it's probably going to come up in some form or another in one of the FRQs. So just to go over some other ways of saying this exact thing, there's less variability in larger samples. There's more variation in smaller samples. Larger samples vary less. Smaller sample sizes vary more. Larger sample sizes provide more consistent estimates, okay, because the distribution is going to get skinnier. We're going to have more, our estimates are going to be more centrally located close to the mean. For example, let's do 2 actual AP tests, multiple choice problems. So in this one, we have a large corporation. It's telling us the distribution of years of employment for employees at this company has a mean of 20.6 years and a standard deviation of 5.3 years. They take a sample of 100 employees. They survey them about employee satisfaction and find that in this sample, the employees had a mean of 20.3 years and a standard deviation of 6.1 years. Now, going back to what we had just talked about, the sample is going to be an unbiased estimator of the population mean. So we expect that to be pretty close to the actual mean, and we see that it is. Right. If we create a sampling distribution, so we do this whole thing over and over and over again. So we take another 100 people, another 100 employees. All right, we find the average of those. Okay, do it again, do it again, do it again. They're going to pile up around the true mean of the population, and the true mean is 20.6. Okay, so this is for the sample, but for the sampling distribution, the more times we do this, the more results we're going to get right at that true population value. Okay, so yes, the mean of the sampling distribution is 20.6 years. That's what he's saying. He is correct. And lastly, a recent study was conducted to investigate the duration of time required to complete a certain manual dexterity task. The reported mean was 10.2 seconds with a standard deviation of 16 seconds. Suppose the reported values are the true mean and standard deviation for the population. So we're starting off with this, centered at that true mean, standard deviation of 16. Okay, but you see in this last sentence here, we have a random sample of 144 subjects. So we're not talking about individual people anymore. Okay, we're talking about 144 of them. What's the approximate probability that the mean of the sample will be more than 11 seconds? So this is really telling us we're dealing with a sampling distribution. Okay, we're not talking about individual values. We're talking about the average of these 144. So it's going to mimic this distribution, but the only thing that's going to change is that standard deviation. We're going to take that standard deviation, we're going to divide it by the square root of that sample size, and we're going to get 4/3, which is 1.33. So our new distribution, once we realize that we're talking about this group of 144 people, it still stays at 10.2, centered at 10.2, but our standard deviation is no longer 16. It's gotten much smaller. It's now 1.33. Okay, what's the probability that it will be more than 11 seconds? Okay, so 11 is here. We want to find a z-score for 11. Always subtract the mean from that z-score and divide that 1.33. And then we're going to use that to find a normal CDF. And I'm going to make you wait as I plug this into my calculator because I didn't do it ahead of time. So I got a z-score of 0.60 over the normal CDF. That goes in lower, 99 for upper. Paste it out and we get 0.2743. Looks like that is our answer there.